great, thanks. All right, so let's start talking about minimal theories. So we want to talk about sort of nice classes of sets. So let's define sort of what a class of sets should mean. And a nice way to say that is the notion of what a structure is. So a structure, S, for us, is going to be a collection of subsets Sn for each n, and Sn is going to be a subset of the power set of R to the n. So, power set 2 to the R to the n. Okay. So a collection of subsets this. They're all positive integers n, satisfying a bunch of properties. So the idea is essentially big enough to handle sort of reasonable logical construction. So first of all, you want it to be closed under Boolean operations. So it's closed under Boolean algebra. So in other words, if A, B are subsets of R to the n, which are in Sn, then A intersect B, A union B, and A complement, all of these guys are also in Sn. Okay, so the first thing you want. So secondly, you want Sn to be closed under existential and universal quantifiers. So what does this mean? It just means that if A is in R to the n plus 1, is in Sn plus 1, and you let pi from R to the n plus 1 to Rn be the projection map, so forgetting the last coordinate, then pi of A is in Sn. Okay. So if you think about it, this means it's closed under existential quantifiers. So if another way to say this, i.e., the set of x1 through xn plus 1, through xn, such that there exists y with x1 through xn comma y in A is in Sn plus 1, is in Sn. Right? Now we also want to be able to put a for all here that actually follows formally from this. Okay? Because putting A for all y here is the same as taking complements, projecting and taking complements again. Okay. So that's one, there's two, and now we need two more things. So we're able to combine stuff. So if A is in Rn, B is in Rm, and A is an element of Sn, B is an element of Sm. A and B are both definable in our structure. Then A cross B, which is a subset of R to the n plus m, is an element of Sn plus m. So you have to take products. And finally, this is a bit of a technical condition. So if sigma is a permutation, denote by, let's call it sigma tilde, the corresponding map from Rn to Rn, which produces the coordinates. The corresponding map. So let me just say the map sigma tilde of x1 through xn is x sigma 1 through x sigma n. Then A is an Sn, implies, in fact, is equivalent to sigma tilde A is an Sn. You can jump off the coordinates. Okay? Okay, and that's it. That's all it takes to be a structure. Okay, and what we say, so we say A is definable, so if A is a subset of Rn, we say it's definable in S, when A is an Sn. Okay? So a structure is just somehow a formalization of allowable subsets in every given dimension satisfying some compatibility axioms. Okay, questions before we move on? It's all very formal and simple in some sense, but just to make sure. Okay. Okay, so just like as an example of the power of these kind of axioms, so we'll just say, or let me make a definition first. So say if A is an Rn, B is an Rm, A, B are definable. Related to some ambient structure we have. And f is some function between them. Then we say that this function is definable if the graph of f so x and A, x equals y, y and b, inside r to the n plus n. Is definable. Okay? Okay. And so let me just make one more assumption. So standing assumption for us, this isn't technically always imposed, but we want the equality operation to be allowed. So we're always going to assume that the diagonal in R squared is definable. Okay? Okay, so corollary, if this is the case, so if you have functions f from A to B and g from B to C are definable, and so is their composition. And so is f composed with g composed with f. From A to C. Again, it's not hard, it sort of just follows from a couple of the axioms. Quickly go through the proof. So let's say A is in Rm, B is in Rn, C is in R to the K. So what you can do is you can look at gamma of F cross gamma of G in R to the power of m plus 2n plus k. Okay. And now you can also look at the set. Let me call it. Let's call it D. So this is definable. Because this is definable, and the product of definable things is definable. And you can look at D in R to the n plus 2n plus k, which is defined to be the set of things. So x, so xm, yn, zn, wk. These are coordinates with m and k bar to them. Such that the vector yn is equal to the, let me put vectors here to make it clear that all vectors with these dimensions. So this guy is definable because it's product of a bunch of diagonals and entire sets, and then you remove some coordinates. So therefore, gamma of f cross gamma of g intersect d is definable. And what is this guy? It exactly consists of guys of the form x, f of x, f of x, g of f of x, right? And so therefore, now you can take this guy, let's call this E. Now you can project E onto R to the m plus k. By repeatedly permuting and projecting one coordinate at a time. And if you do this right, you get exactly the graph which decomposed with f. And it's definable. Okay? We really wanted to show. M plus k, yeah, that's right. Thanks. Okay. So let's really play around these axioms.
So
Yeah.
that's a dumb question. Like, if you start with like the whole space Rn is always in your structure.
Yeah, because it's a Boolean algebra.
Oh, so
So I didn't write that down, I guess, but Boolean algebra is closed under intersections and unions and the empty set. And elements in the empty set.
Oh, okay. No, because I was curious. Because once you have the diagonal, then that follows by projection.
Yeah, that's by projection as well, yeah.
But
right.
I wasn't sure if you needed that section.
Okay, so another definition, which ends up being useful. So structures are really hard to specify because they're extraordinarily large. You have like tons of subsets in every dimension specifying much properties. So the easiest way to specify them, you define a pre-structure S is a collection of subsets Sn in 2 to the r to the n n at least 1 satisfying no properties, just a bunch of subsets. Let me call this S prime, just so I don't change notations. And then the structure S generated by S prime is the minimal structure containing S prime. So you throw in a bunch of sets, then you throw in everything else you have to in order to get a structure. Now, it's not a priori clear that you have a minimal one. So you can do it in 2 ways. You can either show that if you intersect the structures, you get a structure of hard, or you can actually just define S by throwing in all these sets sort of superinductively whenever you're missing one. Just like a standard Zorn's lemma kind of thing. And those structures aren't that big. They're only like 2 to the 2 to the 2 to the r or something. They're fixed cardinality. So there's no issue with any induction scheme arguments or anything, if you care about that kind of stuff. All right. As an example, let R sub less than denote the structure generated by the less than function, which means that generated by the set xy such that x is less than y in R squared. So we define the pre-structure by throwing in the diagonal, we assume it's always there, and this subset here, and then we sort of just throw in everything else we need to know to make it a structure. Okay?
So S prime N's are just any subsets, right?
S prime is just any subset, yes, that's right. And so how to think of like the structure generated by this graph here? It's exactly all subsets you can define by writing a first order formula involving only the operations less than and equality. Right? You can use for all there exists less than and equality and ands or ors. And that's really what you get for x is less than y. And so, sort of what are the elements of sets in x is less than y? So, well, let me throw in something else. R less than denotes this, and maybe I should have thrown this in before. So I want to allow make one more assumption that we haven't made so far. Assumption 2 is all structures and pre-structures so contain all finite sets. Let's not throw in the finite sets in R. Just the points are allowed to be in a structure. So basically, I want to allow my formulas x equal a constant. That should be a thing that we're allowed to do. Okay. So A in Rn is definable in the structure R less than if and only if A is the union of finitely many sets AI where AI is defined by imposing finitely many relations of the form so there's three things you can do. So you can set a coordinate, let's say xj is equal to some constant. You can set two coordinates equal to each other. You can set one coordinate bigger than another. And you can set, well, I guess actually, the other one's symmetric. Okay. Yeah. This is all that that you can do. Okay? So it's not hard to check this, but it's not sort of totally trivial either. And the main thing, you can certainly sort of get all of these guys, because you have the x equals y graph, you have this graph, you can project, intersect, project and stuff. But in theory, so I'll write this as an exercise, I'm not going to do. But in theory, you're allowed to do all sorts of weird things as well, right? You can project, take complements, project again. So you can write things like there exists x such that for all y, for all z, z equals c, and like x is bigger than y, or x is equal to y, and z is bigger than x. Right? Like this is some sort of crazy long formula which isn't automatically written in this form. So you have to like do some what's called quantifier elimination to show to prove that you can write things in this form. Okay. Okay, so that's sort of the very basic idea behind structures. And so structures are sort of very large, and they capture the notion of like everything you can possibly do, allowing some basic operations or some basic sets sort of really well. They formalize that idea really well. So let's define an O minimal structure. So structure S is O minimal which you read as order minimal. Okay. If S is an extension of R less than, so you want it to contain less than operation, such that, and this is the real restriction, so A is in S1, so A is if A is in R, then A is definable in our structure, if and only if A is a finite union of intervals. Let me write it as A is a finite union of points and open intervals A, comma B, where A, B are in R union plus minus infinity. So like semi-open intervals on either side are fine as well. Okay? Okay. So that's what it means for a structure to be O minimal. Now, a couple comments about this. One is we're only going to care about structures where you can add and multiply as well. We don't need that for the definition, so we're going to leave that out for now. A lot of the theory doesn't really care about that so much. B might sort of seem a little weird that we're only imposing a restriction in dimension 1, sort of the most simple sets. Sort of, in theory, you can imagine that like, well, S1 maybe is like as simple as it can be. Certainly anything containing R less than has to contain these guys here. But maybe like S2 or S7 is like super complicated, and that's bad. But somehow the point is, if you control S1, you implicitly are controlling all the ascends because you have the projection map. Right? And so it's not totally clear at all, but if something is like, you have a really crazy set inside Sn, then you have really crazy sets in S1, ends up being the point. Yeah. All right, so it turns out that imposing O-minimality in your structure makes it super nice in a bunch of different ways, which we'll talk about. So like example, so the graph of the function y equals sine of x, which has been our enemy for a while, is not in any O-minimal structure. Because if you have y equals sine of x, you can intersect with y equals 0, and that gives you a bunch of different x's, infinite set of x's, which is not as a form of finite median of points and intervals. So automatically bad. Is that clear? Cool.
So people in like logic or something study these structures?
Yeah, it comes from model theory.
Okay.
In logic, yeah. I mean, they study a bunch of different structures. Not all
This
O-minimal.
particular one works well with.
I'm sorry?
I guess so. They study lots of different structures, but this particular one works well with what we're going to talk about.
Yeah, that's right. Somehow O-minimal structures are like the simplest possible structures.
Oh, it is.
Yeah. So in logic, somehow, in this sort of world, like O-minimal is somehow the simplest possible thing in many ways. And then containing the integers is like the most complicated possible thing. Because the integers are like uncomputable and undecidable and stuff, the Hilbert's problems, and so like containing z is really bad. There's lots of stuff in between, which they also study. Yeah, but this, I mean, I'm not a logician, so I don't really understand the theory super well. But like a lot of what they do in logic is they study things in some amount of generality, and then they use like compactness theorems to prove stuff. So like an example of a theorem which is secretly logic, but maybe don't think of as logic when they come across it, is like the axe-Grothendieck theorem, if you've seen that kind of thing. Like this idea in algebraic geometry that like all algebraically closed fields greater than 0 are like the same, and so you might as well deal with Q bar, or you might as well deal with the complex numbers. This sort of, what's really happening is you have some structure, for example, a field, with some axioms, like algebraically closed, and you prove that like all models of this structure behave the same way. And so that's somehow proving something about one model, proves something about the theory. So this sort of basic trick is what logicians do, which is why sort of O-minimality ends up being powerful. Okay, ready? Yes.
What's the structure? You can just take R less than and throw in all such ways and then extend the structure.
R less than contains all these A's. Right? If you have the less than operation, you can define open intervals and you can define points and you can take finite unions. Yeah. So R less than already contains this, and basically the minimal word is supposed to mean that you don't contain anything extra in S1. Okay, so it turns out that O-minimal structures only contain, in some sense, really nice subsets, because we want. So what I want to do is I want to prove a couple of things for you about O-minimal structures. So ultimately, I want to show, we'll be on like a journey to show that the functions, the elements, the functions from R to R, or some subset of R to R, which are definable in some O-minimal structure, are essentially continuous. In fact, essentially smooth in some sense, which is kind of weird. But I want to explain, so to give you an idea of how it follows from these axioms. Okay. So So let me state the theorem first. And then we'll prove it. So let f, suppose f from R to R, you can impose subsets but of the main definition, but it doesn't actually matter very much. So let f from R to R be a definable function in some theory S, which is O minimal. An S, so an O minimal structure. Then you can break up R into finitely many intervals. So then there are finitely many disjoint open intervals. I1 through Ik, which are almost R, such that their union is cofinite. Okay. Such that for each such interval, if you look at the function f restricted to ij, from ij to R, then this is either so constant or monotonic and continuous. Okay? Just by imposing this, already your functions can't sort of be that great. You can break up finitely many pieces, and each one is either constant, or it's increasing continuous, or decreasing continuous. Okay? And you can see pretty easily that, so first of all, you shouldn't be able to require continuity, because a function which is 0 everywhere except for its 1 at 0 is like a perfectly reasonable function. You can find Rx already. So certainly finitely many pieces is necessary, and also like you shouldn't be able to require monotonic everywhere either, because you can certainly go up a little bit, then down a little bit, whatever. You can just specify what happens. Like given a composition like this, you can specify what happens with each of these pieces independently from each other. Okay? But this is a typical type of theorem that you see in homeomalities. You can sort of break up into finitely many pieces where something reasonable happens. But it's no, you sort of can't do anything more than that. Okay, so let's prove some stuff. So lemma. We can start with, we'll finish next time. So suppose I and R is an open interval. Is an open interval. And f from I to R is definable. So I'm not going to write in S anymore. Everything is definable with a fixed O minimal theory. S we're talking about. definable such that x is less than f of x for every x in I. Okay. Then there exists some subinterval of I, J an open interval, and a constant C, which is bigger than J. C is bigger than every element of J. Maybe I can write C is bigger than sup J. Such that f of x is bigger than C for x and J. Okay? In other words, you have a function I, which is bigger than the identity function. You can pick some subinterval where it's like uniformly bigger. So in the entire interval, it shows it something bigger than the whole interval. Okay? So, okay, let's prove it. Okay, so let I be AB. For notation's sake. And write B to be the set of D in your interval such that f of x is at most f of D for all x in the interval AB. Okay? In other words, look at all these, which are sort of maximal up until D, which f is maximal up until D. Okay, so I'm not going to write the axioms to prove it, but B is definable, right? You can write B with quantifiers, right? B is a set of all D, such that for all x, satisfying x is less than a, and x is bigger than D, f of x is at most f of D. So B is automatically definable. And so because B is definable, and it's one-dimensional, subset of R, B is automatically a union of finitely many points and open intervals. This is how you use the omnidimensionality axiom. Define interesting sets which are one-dimensional, and you say, well, there aren't so many of these. Okay, so now we have two cases. So the first case is there exists an epsilon bigger than A, such that A epsilon is in B. And the second case will be there exists an epsilon bigger than A, such that A epsilon is not in B, is in the complement of B. Okay? Any open interval is either inside. Anyways, yeah. Okay, so if this is true, what does this mean? Well, this means F is increasing. On A epsilon. Okay. Because for every element in A epsilon, F is bigger than everything before. That's what it meant. So now, so take J equals some alpha beta in A epsilon with, so you want A to be less than alpha, which is less than beta, which is less than f of alpha. f of alpha is bigger than A. So pick any numbers in between. Now you can take C, the f of alpha. Okay, so because f is increasing, f on here is because sorry, I think it's a mistake. So yeah, because f is increasing, f on anything in between here is bigger than f of a. This is f of. Oh, sorry, I miswrote. Yeah, this is f of a, right? No, this is f of alpha. So because, sorry, one second. So f of x is bigger than c. Yeah, no, that's right. Yeah, so f of alpha is c, and f of anything inside alpha beta is bigger than c. Just wanted to show. Yeah, and c is bigger than anything inside the interval. So that, in this case, is that. Okay, and case 2 is not case 1. So not case 1. So in this case, then there exists epsilon bigger than A, such that A epsilon is in B comma. Okay? This is how finite unions of intervals and points work. Okay? So okay, so what does this mean? This means for every point bigger than A, there's something inside there which is bigger than that point. So now we can take, so then there exists T naught inside A epsilon with f of T naught bigger than f of epsilon. And then you can define Ti. So proceeding in this way, inductively you can find an increasing sequence or decreasing sequence the whole thing is bigger than A, such that f of such that, let me write, C is bigger than f of T0, which is bigger than f of T1, and so forth. Done. So pictorially, what's sort of happening? Here's our interval AB, and here is the identity function. This is the graph of x equals y, and here is our point epsilon, and so we're finding a sequence of points here, such that I've gotten confused myself, sorry. So you can find this such that f of T naught is anybody see my mistake? It should be like pretty easy now, but I messed up somewhere. Okay, I'll finish this case next class. We'll continue. Sorry about that. Okay. Questions? All right. So case 2 to be finished next class.